So please give a warm welcome to Luke. Thank you.
All right, thank you. So, imagine getting alerts from your observability system. You look at your dashboards and everything is red. Your critical jobs are failing. You're scrambling to fix them, and leadership wants answers, and your customers are feeling the impact. A few years ago, that was our reality. I'm Luke Hackett, Principal Engineer at Sky, and today I want to take you on our cloud-native migration journey. A journey that had us migrate from a Spring Boot monolithic app to a cloud-native, event-driven system that now executes thousands of jobs per minute. But before we delve into the architectural decisions we made to help us kind of move away from firefighting to future-proofing, I wanted to provide some context as to what we do at Sky. So our mission is really to become the leading entertainment platform, delivering unique, personalized experiences at the heart of every home. Now, the team I'm part of plays a really huge role in making that happen. We build a content management system that empowers our partners' global editorial teams to showcase the very best TV shows, movies, and live sporting events. These editorial teams were creating rails of content like the featured rail or live sports this week. But here's the challenge. Across the globe, these teams were manually building hundreds of these rails every week. It was slow, it was boring, it was repetitive, and it just frankly didn't scale. So we asked, what if we could automate this? What if we could generate rails based upon editorially created queries? And that's how we came to invent something that we called can searches. So a can search is effectively just a query with an execution cadence set to it. So a query gets executed on a schedule, such as live tennis this week. Editorial teams use our in-house query building tool to create these queries. They can pick from a range of filters, such as program types and genres, channel providers, and more. Once configured, our Spring Boot application would pick up these can searches and execute them based on their configured schedule. The job would then send a query to our content discovery APIs. And those APIs would curate the perfect content mix. Our Spring Boot application would then receive that response, cache it for optimal delivery. That then cached content gets delivered straight to our customer devices, whether it's Sky Glass here in the UK, Comcast Xumo proposition in the United States, or Rogers Ignite in Canada. The result? Customers always see fresh, relevant content every single time they turn their devices on. Now, while our Spring Boot app helped us get can searches off the ground, its usage increased, and that's where some of our cracks started to appear. And those cracks revealed some fundamental challenges that were holding us back from developing this solution further. So first was tight coupling. Our execution logic and our scheduling logic are actually embedded in the same application. So that meant that if we changed one part, it risked breaking the other. It also made it really hard to evolve or reuse those components independently. Scalability. Even though we deployed our application across multiple nodes, only one node could actually execute the jobs. So when we needed to scale, it meant that we had to scale everything, even the parts that weren't doing any work. That drove up our infrastructure costs and just made things more complicated. Third was observability. We really had limited visibility into job statuses, their failures, and whether or not they were performing in a reasonable amount of time. Debugging was painful. Logs were really noisy, and we could rarely find the root cause analysis. And finally, fault tolerance. So when our jobs failed, they often required our engineering teams to manually intervene and try and figure out what was going on. We had some basic retry mechanisms, but no real safety net. These weren't just architectural limitations that held us back from scaling and supporting more propositions. So once we understood the pain points, we knew that we couldn't just apply some patches and fixes to the existing system. We had to have a complete rethink. So we stepped back and we kind of asked, what kind of architecture would let us scale globally, recover gracefully, and operate far more efficiently? And that led us to 4 guiding principles, our North Star for every design decision we were about to make. So we wanted scalability by default. We didn't just want to add more powerful machines, but we wanted more flexible infrastructure that can handle increasing workloads much more smoothly. Second, we wanted to decouple our workloads. No more single node execution. We needed to break apart the scheduling and processing so each can evolve and scale independently. Third, we realized that event-driven was probably the way we wanted to go, simply because of the flexibility and the scalability that those architectures bring. We wanted a system that could react when events happened, rather than it trying to predict things and upfront computing things. And finally, observability. We wanted visibility into what our system was doing. We wanted metrics and alerts at every single layer within the application to ensure nothing slipped through the cracks. And these were our 4 foundational goals for our system, ensuring that we could support our partners, our editorial teams, and customers all at scale. So with our goals defined, scalable, decoupled, event-driven, and observable, we kind of stepped back and asked, what does an architecture that embodies these principles look like? So we've got a big picture on screen. We are going to deep dive into some of the aspects here. But before we do deep dive, let's just quickly kind of have a run through of the higher level picture. So we have our scheduling components. These are the components that schedule events to be executed. We make use of a Lambda function to generate the events and have them sent to Event Bridge, which routes events to the correct job handler. Next, we have our job execution components. We built them using SQS and Lambda, powerful services that let us scale horizontally, running many jobs in parallel. We also, at this point, baked in observability right into these components, from dead letter queues that caught our failed jobs, to CloudWatch metrics and real-time status updates. We wanted full transparency in this area of our ecosystem, and we wanted a full understanding of what everything was doing at all times. And finally, we have what we call our tooling and delivery components. These are really crucial pieces to our architecture. But to kind of keep things a bit focused today, we're not going to deep dive into these, but just to give you a quick snapshot, this includes our Query Builder UI, which is the UI that our editorial teams use to create the queries, and various APIs that deliver the Rails straight to our customers' devices. So let's take a deeper dive into scheduling and routing. So in our legacy system, scheduling and job execution was driven by cron expressions running on a single node. That was just far too centralized. Created a bottleneck and made scaling really painful. We needed something more dynamic and distributed. So we started reimagining scheduling using Event Bridge at the very core. And here's how it works. So we have a Lambda function that kind of acts as our scheduler. It reads job metadata from our database and generates job events. It executes every minute, but it's looking ahead for jobs that will need to run in the next few minutes. This gives us a little bit of a buffer window, so we're able to queue jobs up, ready to be executed at the right time, without missing anything critical. These events are then sent to Event Bridge. So Event Bridge kind of plays the role of a traffic controller, routing each event to the right job, based upon our predefined rules and targets that we've established. And if a event doesn't match a rule, well, we send it off to CloudWatch for alerting. So we can catch misconfigurations or any surprises before they become problems. One architectural win that we banked here was decoupling. So the Lambda scheduler doesn't need to know anything about the downstream targets where to send the events to. EventBridge inspects the payload on each event and decides where to send it to. And one of the best parts of this is that EventBridge at retail prices is priced at $1 per million events. So it effectively adds very little to zero cost pressures to our architecture, but helps us to keep it simple, scalable, and serverless, which is exactly what we were after. So moving on to job execution, this is kind of where the real work kind of gets done, and there's kind of a lot to go through here. So each of our jobs is routed to its own dedicated SQS queue. And the queue has a Lambda function attached to it with its own code base to handle that job type. This separation gives us agility. We can evolve our job logic in different ways without risking other parts of the wider system. And thanks to our fan-out processing, which we get as part of using Lambda and SQS, we're able to process multiple jobs in parallel across multiple Lambda instances, so we're unlocking that horizontal scalability. If one job spikes, let's say it's waiting on one of our upstream services, it's being a bit slow, it doesn't block all the others. It's kind of like having a team of workers instead of just one, each picking up a task, getting it done. And to keep those workers efficient, we had to do some fine-tuning of our Lambdas. We are heavily invested in the Java ecosystem, and Java Lambdas are not really particularly well known for being highly efficient and fast. So we had to do some magic to get them as fast as possible. So some of the things that we focused on was keeping our Java dependencies lean, keeping the class path as small as possible. We heavily utilized Java static initializers to preload shared resources and connections and things like that. And we set our memory allocations high enough to reduce our overall execution times. That might sound a bit strange, but with Lambda, the more memory you allocate to a function, the more CPU you get. And that helped us with reducing our execution times. We didn't just build for speed, we built for visibility. Every job writes back to Aurora, marking its status as in progress, complete, or failed, along with any number of retries attempted. This gives our engineering teams and our editorial users real-time insights into exactly what their job is doing and whether it's still running, whether it's stuck, or if it's been completed. And of course, not everything goes to plan. Failures do happen. And instead of pretending they won't, we kind of built for them. So every SQS queue is connected to what we call a shared dead letter queue, or a DL queue. It's kind of a safety net for those jobs that don't make it even after multiple retries. From there, we have a dedicated Lambda function that steps in. It logs the execution as failed in Aurora and pushes any additional logs and metadata to CloudWatch. This helps to make sure that the issue is visible to our teams. So jobs don't get dropped or ignored. They are caught, they are logged, and they are queued up for investigation by our teams. But catching failures is kind of only half the story. What we really wanted was to see problems before they turned into incidents, right? And that's where observability comes in. So as part of our observability strategy, we wanted to surface what was working, what was failing, and what needed attention. From infrastructure metrics all the way through to individual job level insights, we wanted complete and utter transparency at multiple levels. So at the infrastructure level, we kind of track all the key metrics that I think most are probably familiar with: SQS queue lengths, Lambda errors, throughput, etc. So we can capture any bottlenecks before they actually become incidents and react. We use CloudWatch metrics quite extensively to pull out key events and information from logs, such as job failures, number of retry attempts, and any execution times. For the critical metrics, though, like the number of jobs waiting to be processed, we've set up a number of alarms. Those alarms are configured to notify our teams immediately once they are breached. And all of this feeds into various Grafana dashboards. And the idea there is that we're pulling data from multiple sources, not just CloudWatch, giving engineers that single source of truth for our overall system health. This helps our engineering teams, empowering them to make faster decisions when incidents do happen, and overall helps to try and spot incidents way before they even are allowed to happen. So observability isn't just for engineers. We wanted our editorial teams, our users of our software, to have the same level of confidence and clarity that our engineers were getting. So what we did is we took some data from Aurora, which tracks our job statuses and retry counts, and we took some data from CloudWatch, the execution metadata history, errors, etc. And we combined them into a single editorially friendly view, similar to the one that you see on screen. We built this directly into our tooling so that our editorial users can log in and check the status of every job at a glance. There's no more guesswork, there's no more raising JIRA tickets, waiting on engineering, Slack messages that never get read. It's just pure, simple visibility for the for the editorial users who use our software every day. But visibility alone doesn't necessarily guarantee reliability, which is also something that we need to think about. So imagine this, hundreds of Lambda functions spinning up in parallel, all trying to connect to the Amazon Aurora database at the same time. It's like rush hour on the motorway, everyone merging into the same lane at once. Just like rush hour, this causes traffic jams and congestion. Aurora has a maximum number of allowed concurrent connections. When we hit that ceiling, that limit, and we actually did, our jobs start to fail very quickly. These failures aren't actually due to any bad code or broken logic. They were actually architectural failures. It was the result of us scaling one part of the system, job execution, without really fully considering the load on the downstream services like our databases. So how did we fix this? So we introduced Amazon RDS proxy. It's a fully managed database proxy that sits in between our Lambda functions and Amazon Aurora. If Aurora was our motorway, then RDS proxy was that on-ramp traffic light signaling system, controlling the flow, managing the connections, making sure everything was staying smooth. So instead of hundreds of Lambdas each opening their own connection directly to RDS, they went through Aurora, they went through RDS, and RDS proxied and pulled them to Aurora. Now hundreds of Lambdas can run in parallel without overwhelming the database. And the best part, we didn't have to rewrite our database integration code. It was a very simple plug and play win. It's the kind of invisible win that boosts reliability without even increasing our complexity. It was a really, really small change, but it was a massive, massive impact. And it was one that allowed us to scale much more quickly with confidence. So, just to kind of quickly recap, we replaced our kind of old legacy monolith Spring Boot application with a pretty flexible event-driven system. We nailed our job execution with SQS and Lambda, decoupling it and unlocking horizontal scalability. And we embedded observability throughout multiple layers of our application. Not just for our engineering teams, but for our editorial users as well. All of this gave us a much faster, more resilient and transparent system. But there was still a pretty big challenge left. And the challenge was simply, I think, one that we've all probably faced before, which is how do you migrate a legacy system that's handling a lot of traffic in production to the new system without breaking anything? So we made kind of 4 key decisions to kind of think about how we wanted to achieve a safe and smooth transition from the old system to the new. The first kind of decision we made, and we made this very early on in the development process, was to actually keep the existing database and schema and its data. We realized that we didn't need to change the database, so we didn't. Reusing the existing structure and the data that comes along with it massively reduced our complexity and just helped us move faster with far less risk. Second, we ran both the systems in parallel. The old application and the new serverless one ran side by side. This gave us a couple of advantages. One, it gave us a bit of a safety net. We could always fall back if we needed to. But two, it allowed us to validate the new system under real-world conditions before pulling the cord on the old one. Third, I know everyone says this, but no big bang rollout. I'm sure everyone's heard of this before, but we really did avoid a big bang rollout. We transitioned very gradually, rolling out by individual partner and job types, and monitoring each phase very carefully. And finally, we built what we called an output comparison test suite, which is basically one of the most valuable pieces of the thing that we actually built in this project. This test suite helped us validate the outputs of the new system against the old. We used it to test any edge cases, and it gave us the confidence that the new system was fully compatible with the old and it could stand on its own. But how did this test suite work? So if we kind of compare the old, I know this is very, very high level here, but if we compare the old and the new systems kind of side by side, there was one thing that we very quickly identified. The legacy system and the new systems were both reading from and writing to the same database. Any update made by one was instantly visible to the other. We realized that we could use this shared source of truth as a bit of an advantage to us. So what we built was essentially a live output comparison tool. Think of it a bit like a continuous functional test. It pulled each job from the database and fetched the generated outputs from both systems. It would then compare the outputs line by line. We integrated this as part of our CI/CD pipelines, not necessarily as a build breaker, that would be somewhat counterintuitive, but more of as a silent signal, kind of using it to help us catch implementation differences and helping us guide to getting to 100% compatibility. After each comparison, the test suite generated a final score, and we treated that, as I say, as our own internal confidence meter. When that figure hit 100%, we knew we were pretty confident that the new system was able to stand on its own and we could start migrating. So, kind of before we wrap up, just wanted to kind of leave with, say, 4 key takeaways that we kind of took on this journey. The first one is build for scale, most definitely, but think end to end. Yes, we decoupled a lot of our components with Lambda and SQS, and yes, it unlocked horizontal scalability. That's something that we were absolutely paramount on getting. But it also taught us an important lesson. True scalability means looking beyond individual components with your overall architecture. You have to kind of consider how scaling one part of the system may impact another part. Next, observability. It's not optional, it shouldn't be an afterthought, it's 100% essential. We embedded observability into our application at multiple layers, and we didn't just expose that for our engineers, but we exposed it for our users too. The real-time visibility aspect really helped to build trust and helps us catch issues, reducing downtime and support tickets. Remember, if you can't see an issue, you can't fix it. Reliability is all about resiliency. It's not about perfection. Things will fail, and that's okay. What matters is how your system recovers. Do you have the necessary steps to kind of recover, ideally in an automated way? By adding safety nets like DL queues, RDS proxy, and some of our visibility, we made our system much more resilient and self-healing. And finally, migrate with measurements, not with hope. We didn't flip a switch and kind of hope for the best. We ran both the systems in parallel. We verified the outputs pretty rigorously with our automated test suites, and we rolled out gradually, bit by bit. When our data and test suites told us that we were to go, we moved, and we moved confidently. So we didn't just embark on a cloud migration journey. We took the opportunity to change how our teams think, how our partners operate, and ultimately made our customers' experience far more reliable. And with that, I will leave it at that. Thank you for coming along.
Oh, fantastic. Loved the talk, loved it. We have time for a few questions.
So you centralized all of your data over loads and loads of different tasks into one system, well, into one database. How did you manage your redrive behavior?
So the question was if we've...
So you've centralized all of your data from your tasks. How did you manage your redrive behavior for your lambdas?
So the retry, each of our tasks have a different type. So we have type A, B, C, etc. And each of those can have individual SQS queues, and the retry logic is different per queue, right? So we don't say all get 3, some only get 3, some may get 5. It really depends on the upstream services, what we're dealing with. Some have better data and APIs than others, which is why we kind of have that separation.
So after you've been through the retries, there's no other way for you to restart a job if something's changed? It's just dead after that?
No, you can. So I didn't go into the tooling too much, but inside our tooling there is a run job now piece of functionality, which effectively what that does is that tells the scheduler to, hey, this job, can you go and run it immediately? And it just throws it into the queue immediately. So you can manually force things through if you need to, yes.
Okay, I get what you're doing. Thank you.
Right. Any more questions? I have a question. I'll come back. So, Luke, you mentioned that as part of the migration is pretty much the business logic was rewritten, right? But why did you choose Java, knowing that Java Lambda combination probably isn't the best compared to others?
So a lot of the logic we had was written in Java already. And our team are a Java-based engineering team. So it made sense to stick with Java rather than moving to something else, was the short answer.
Okay, understand. Yeah.
Follow up on your question, could you share more insights about the Java Lambda? And my team, we gave up using Java Lambda because we need it in a real time. And the warm-up was like 2 seconds, which is not suitable in our case. When you increase the memory, how it fast become?
Yeah, so it's actually a really interesting question, actually. And I actually think there's probably several papers one could write on this, because it's a fascinating area. So there are kind of 2 areas when your Lambda's booting up, right? You've got the cold start time, and to get that down, there are a few tactics you can do, but the main one is dependencies, class paths, and things like that, right? Once the thing is running warm, you're pretty much on a par with other languages, right? So the real objective is get that start boot time down. When we were doing the initial development in our sort of lower dev environments, we were running quite small memory usages. I can't remember exactly, but it was something like 500 or so meg. And we were seeing jobs taking a minute and a half, right, which was pretty long. The moment you start tuning that memory up, and I think we got up to, I can't remember if it was 4 gigs of RAM, I think we got up to, we're down to like below sort of 15 seconds, which for a job that runs in the background is perfectly fine for us. Obviously, if people are looking for something a little bit more reactive, then that may not be sufficient. But yeah, there is definitely a scale. As you scale that thing up, you definitely see that execution drop pretty quickly. There is a link somewhere I saw on, I can't remember if it was a blog post or on AWS, where somebody's actually done the analysis and they've worked out that if you set it to, I think it's 1536 MB, that immediately gets you 1 CPU, and they've actually worked out what levels 1 CPU is, 1.5, 2 CPU, etc. There is a blog post on that.
Okay, final question.
Yeah, so you showed everything using Aurora, and you showed a really specific problem about Aurora, which is the scaling. Was there any reason that you picked Aurora over something like DynamoDB? Did you have any sort of relational requirements?
So we could have, yeah. We could have also choose MongoDB or any, like there's a multitude of ones. For us, there wasn't a huge advantage for going for DynamoDB over what we had. As in, what I mean from that is, the way that we were storing our jobs and all the metadata associated to it in Aurora was fine for us when we weren't seeing any limitations. So we took that as a, let's not change that to keep things simple so we can focus on changing other parts where we know there are problems. So it was more of a cost opportunity analysis of, it's not really a big problem, let's leave it, versus let's go all out, if that makes sense.
Yeah, sure. Thank you.